Thank you very much for the introduction and for the opportunity to speak at this conference. Thanks also to my co-workers, Juliana, Tiago, and Guilherme, for their valuable contribution to the development of this work. The title of my presentation is Characterization of Eucalypt Lignoboost Lignin for the Production of Lignin Nanoparticles. As we all know, technical lignins are important precursors for a wide range of biorefinery applications, and these are largely dependent on their physical and chemical properties, including molecular mass distribution, thermal stability, and functional groups residing in their macromolecular structure. Many lignin isolation processes from black liquor are already available in the market. Technologies such as Lignoboost aim at isolating lignin in high purity to make it commercially available for other applications than those related to the traditional combustion for chemical recovery and heat generation. Such technical lignin may be applied as a source of phenolic compounds and as a starting material for the production of carbon fibers, reinforcement fillers, and so many other things. One of such applications is the production of lignin nanomaterials. Nanotubes, nanofibers, and hydrogels have been already produced from lignin, with the nanoscaling process contributing to the formation of aggregates with controlled morphology and particle dimensions. This way, lignin nanoparticles would retain the same chemistry of the precursor lignin, while improving properties such as specific surface area, homogeneity, and thermal stability. In this work, lignin nanoparticles were obtained by nanoprecipitation, and in this case, particle size distribution strongly depends on factors such as the drip speed, drip order, stirring speed, temperature, diffusivity between solvent and anti-solvent, and the solvent ratio. Nanoscaling lignin can also enhance the intrinsic antioxidant activity of these materials by increasing surface area and volume ratio in aggregates with diameters below 250 nanometers. In general, this antioxidant activity depends on properties such as phenolic hydroxyl content, serum-diol-guaiacil ratio, molar mass distribution, among others, with the resulting material being useful for the development of UV protection agents and other related things. With this in mind, we aimed in this work to produce lignin nanoparticles from Lignoboost craft lignin derived from eucalyptus and measure their antioxidant activity. This goal was achieved by first characterizing the precursor lignin. It is important to mention that no purification or fractionation was done to it, followed by the synthesis of the nanoparticles, characterization and measurement of the antioxidant activity using classical methods. This lignin contained a very low ash content, elemental analysis typical of technical lignins, nearly 90% total lignin content, and a surprisingly high carbohydrate content of 12.7%, led by the presence of arabinoglucuronous islands. P31 and NMR revealed the presence of phenolic hydroxyl groups, 3.79%, aliphatic hydroxyl groups, 1.28%, for a ratio between the two of 2.95. Finally, the TG of this lignin was 133 degrees centigrade, and its weight average and number average apparent molecular masses were 1104 and 592 grams per mole, respectively. And this for a dispersity of only 1.87. As one can see, the molecular mass distribution of these lignins was very low for a craft process compared to values already described in the literature, sometimes beyond 4,000 grams per mole. This is the typical P31 NMR spectrum of lignin, in which one sees the quantitative analysis of different types of hydroxyl groups, aliphatic, serum-diol plus 5 substituted hydroxyls, and this because the signal for the two are overlapping the spectrum, guaiacil hydroxyl groups, and also carboxylic hydroxyl groups. And these quantifications here shown provide the 2.95 ratio between phenolic and aliphatic that I've mentioned in the last slide. Lignoboost hardwood lignin was also characterized by HSQC2D NMR experiments, and these are the two spectra obtained for the aliphatic and aromatic regions, both to the left and to the right, respectively. Results indicated the occurrence of a variety of functional groups, some oxidized groups as well, primarily syringil, from which a ratio of syringil plus guaiacil of 4.37 was obtained. Also, it was clear that the low beta-O4 linkages in those lignins was coherent with their low molecular mass. For the preparation of the lignin nanoparticles, two different solvent dripping rates were utilized, 2 mL per minute and 4 mL per minute, and both coming from a solution of these lignins of 1 milligram per ml in THF. And the dripping of those two solutions, I mean, for each one of those cases, two different rates, the dripping was done over KCl 0.01 mole per liter as the anti-solvent. The lignin nanoparticles were then obtained as a suspension after removal of THF by evaporation. Here one sees the size distribution of these lignin nanoparticles done by dynamic light scattering. In this case, it is clear that the profile reveals a bimodal distribution, and the bimodal distribution was led by a much larger population of particles within that range shown in this slide, talking about 50 to around 100 nanometers. This was observed for the two different dripping rates of 2 or 4 mL per minute. Regarding stability, small particles tend to aggregate with time, but their particle size remained close to the range of the leading population of the bimodal distribution. Stability in this case, followed by DLS, was done for 1 day, 15 days, and 45 days. The transmission electron microscopy images that I show in this slide reveal the presence then of hollow particles formed probably by the expelling of the solvent during the precipitation of those lignin nanoparticles, and also after as much as 33 days of storage in suspension, the aggregation of small particles forming these lumps that could be easily taken apart by agitation. The zeta potential was an important measurement in our studies, because by doing so, we were able to demonstrate that the particles were negatively charged at a surface. And that surface remained stable at neutral pH over time. And one sees that the zeta potential at pHs close to neutral and above were around minus 40 millivolts. That is telling us that those lignins, especially in that range of pH, could be considered relatively stable for several probable applications in suspension. We then moved on to the determination of the antioxidant activity of those lignins. In this case, the assay was based on the inhibition of the ABTS radical in PBS buffer pH 7.4 for incubation times as long as 40 minutes. This is the Trolox calibration curve, and one sees that Trolox, used as a reference, provided the highest antioxidant activity right in the beginning at time 0. However, when we did the same for the lignin nanoparticles obtained after precipitation using a dripping rate of 4 mL per minute, higher antioxidant activities were obtained with increased incubation time in the assay. Once again, talking about the calibration curve of Trolox, we could, by considering the data, calculate the EC50 values of Trolox And this corresponded to 7.68 micrograms per ml. Whereas for the lignin nanoparticles, the same value, EC50, was only 4.04 micrograms per ml, showing already that those lignin nanoparticles were superior compared to the Trolox antioxidant. Again, with the data coming from the calibration curve, one could calculate not only the EC50 values, but also the Trolox equivalent antioxidant capacity, TEAC. And it is clear that after 30 to 40 minutes, the highest levels of antioxidant activity of those particles were achieved. And that was probably due to the capacity of neutralizing radicals more efficiently due to the chemical groups and chemical properties altogether with the high surface area of those particles. Compared to other materials found in the literature, our lignin nanoparticles displayed a superior performance. The only material that actually approached the inhibition level obtained with our particles was this nanocomplex between lignin, Kraft lignin nanoparticles with gold and silver nanoparticles. And although the inhibition was as high as 96% for both, inhibition was the same, but then the EC50 for our lignin nanoparticles was much lower. The reasons for such a high antioxidant activity are that these particles have a very high specific surface area, a high total phenolic hydroxyl content, and with that also a good ratio between phenolic and aliphatic hydroxyl groups. The cetinyl to guaiacyl ratio was also high, and cetinyl units are known to be better than guaiacyl units for that specific purpose. And finally, we observed by NMR some oxidized cetinyl units, and those cetinyl units, due to their higher oxidation level, helped the radical stabilization and therefore leading to higher inhibition performances. With this, we hope to have demonstrated that nanoparticles could be produced by nanoprecipitation from this lignin-boost eucalypt Kraft lignin without any further purification, and that the material obtained, regardless of its relatively high carbohydrate content, had a tremendous performance compared to one of the best reference materials available in the market. With this, I'd like to close my presentation by thanking all of those who have supported our laboratory, but my special thanks goes to the RIADICIP group or network. We have had a tremendous networking activity during the last 5 years or more, in fact, but much more, and I'm glad to be part of it. With this, I'd like to thank you once again for your attention, and I'm open for questions if time allows.
Hello, my name is Bruno Valente. I'm a PhD student at the University of Aveiro, and today I'm going to present you my work on bio-based composites reinforced with mechanically treated eucalypt pulp fibers. This work was carried out under the supervision of Drs. Carmen Freire and Carol Vilela from CISECO and Carlos Pascoal Neto from Raiz. I'll start my presentation with a brief introduction on polymeric composites and its challenges. Then I will move to the aims of this work and the methods proposed to achieve them. Next, I will discuss the main results obtained, followed by some conclusions. Polymeric composite market, it's still dominated by composites with petroleum-based matrices, such as polypropylene or polyethylene, reinforced with synthetic fibers such as glass fibers. But unfortunately, those composites are not environmentally friendly. In the last decades, however, natural fibers found their way into the composite industry, replacing the glass fibers, mainly because of their renewability and biodegradability, but also because they have lower density, lower production cost, less greenhouse gases emissions associated with their production, and because they are not dangerous to humans or abrasive to machines during processing. These natural fiber composites, also known as biocomposites, they have already reached the market and are actually produced at a large scale for many applications such as the automotive industry, furniture, home appliances, and even electronics. But although these composites are a step forward in achieving a good sustainability, those matrices are still based on fossil resources, and the composites are not recyclable or biodegradable, which poses some challenges on disposal. So one way of overcoming those challenges is to replace these petrochemical-based matrices for bio-based and biodegradable ones. Of those, polylactic acid, PLA, and polyhydroxybutyrate, PHB, are among the few bioplastics commercially available and with comparable properties to some of the commodity plastics. Moreover, they can also be processed through the common technologies used for other plastics, and the increasing interest on the use of these sustainable polymers for the production of composites is clearly proved by the ever-increasing number of studies in the field. Nonetheless, these so-called green composites, where both the matrix and reinforcements are bio-based, they face some of the same challenges as the biocomposites. Because the matrices are hydrophobic and the cellulose fibers are hydrophilic, this intrinsic hydrophilicity of the fibers combined with their high aspect ratio often lead to agglomeration and bad dispersion of the reinforcement in the matrix. And as a consequence, the visual aspect of the composites is inevitably impaired, as well as their mechanical performance. Along the years, several strategies have been tested with the aim to overcome some of these challenges. These strategies range from physical-chemical treatments such as corona, plasma, or gamma rays, chemical treatments such as mercerization or surface modifications like esterification, whose aim is to decrease the hydrophilicity of the fibers through the incorporation of more hydrophobic groups. Then we also have the use of external additives, as are the examples of silanes or isocyanates, and the efficiency of compatibilization depends on the ability of these molecules to link both the matrix and the fibers through covalent bonds. And another alternative to avoid fiber agglomeration are the mechanical processes such as ball or pan milling. And in there, the goal is to reduce the size of the fibers and improve the dispersion without use of any solvents or chemicals. And in fact, that together with the fact that these processes are easily scalable were the main motivations why we use mechanical treatments for our work. With that said, the aim of this work was to study the effect of the fiber load and the influence of the aspect ratio of micronized fibers in the matrices of PLA and PHB. To study the influence of the aspect ratio, we took bleach eucalyptus kraft pulp and we used a micronization procedure to prepare micronized fibers having 4 different aspect ratios, and those are cellulose 60, 200, 355, and 500. These 4 micronized fibers and the non-treated bleach eucalyptus kraft pulp were melt compounded with 2 different grades of PLA and 2 different grades of PHB for a fixed fiber load of 40%. To study the influence of the fiber load, we use one of the micronized fibers with an intermediate aspect ratio, and that was cellulose 355, and we changed the reinforcement load from 10 to 40%. Finally, all these composites were characterized regarding their morphology, tensile, flexural, and impact properties, water uptake capacity, and melt flow rate. Now moving on to the results and starting with morphology, we know that many of the properties in the composites depend on the ability to transfer energy from the matrix to the fibers, which on its turn depend on the dispersion of the fibers and on the interface between the matrix and the reinforcements. On the plus side, when looking at the test specimens, or even at fracture surfaces of the composites, there are not any visible agglomerates or bundles of cellulose either in any of the composites with different matrices, composites with different micronized fibers having different aspect ratios, or even composites with different fiber loads. And this is a clear indication of the good dispersion and wettability of the micronized fibers in the different PLA and PHB matrices. On the downside, despite the good dispersion, the fracture surfaces reveal the existence of some fiber pullouts and voids, which are a sign of the poor interfacial adhesion. And this closer look at the interface also allowed us to confirm superior compatibility of the fibers with PLA than with PHB. And is going to be important to explain some of the following results. So regarding the mechanical properties, and starting with the tensile ones, at first we can see that when increasing the fiber load of cellulose 355, we can also see an increase in the Young's modulus and in tensile strength. And that means that despite their reduced size, the micronized fibers still have a positive reinforcing effect. In fact, the incorporation of 40% cellulose 355 increased the Young's modulus by 3.7 and 3.1 times for the composites with PHB and 2.2 and 2.1 times for the composites with PLA in comparison with the matrices. On the other side, the aspect ratio of the micronized fibers had little influence on the tensile properties. However, as we can see on the red arrows, the Young's modulus and the tensile strength of PHB composites with bleach eucalyptus kraft pulp are inferior to those composites with micronized fibers, and this means that micronization may in fact be a viable method to improve some of the properties, especially in composites with PHB. The results for the flexural properties in the 3-point bend test are in good agreement with the results and the tensile properties. And that means that increasing the fiber load leads to an increase in the flexural modulus, as you can see on the graphic on the left, and the aspect ratio of the micronized fibers had little influence, as we can see in the graphic on the right. Nonetheless, we can see again the inferior flexural modulus of composites of PHB with bleach eucalyptus kraft pulp compared to the composites with the micronized fibers. Both these results in the tensile and flexural properties probably have to do with the effect of the lower compatibility between the PHB and cellulose fibers, as I said before, together with the high aspect ratio of this neon-treated bleach eucalyptus kraft pulp, which leads to weaker resistance of the composites upon stretching or bending. The effect of the fiber incorporation on the impact strength in biocomposites is still unclear, but in our work, the increasing load of micronized fibers led to a reduction of the sharp impact strength, as we can see in this graphic. And although various factors such as the crystallinity and stiffness of the fibers and the matrix can have an influence, the decrease in the impact strength is most likely due to the poor interfacial adhesion between the fibers and the matrix as previously shown. This lack of compatibility leads to crack initiation and propagation, which decreases the amount of force that material can absorb during impact. On the effect of the aspect ratio, smaller fibers seem to favor the impact strength in composites with PLA. On the opposite, in composites with PHB, the aspect ratio of the fibers had little effect. Now looking at the water uptake results performed by immersion during 31 days, we see that all thermoplastic polymers, all PHB and PLAs, they have lower water uptakes, which is easily justified by their hydrophobic nature. But on the other hand, cellulose fibers are hydrophilic, and so as the fiber load increases, so does the water uptake as expected. It is worth noting that PHB-based composites, they have maximum water uptakes higher than the PLA-based composites, which is also probably related with the inferior compatibility between the PHB and fibers that makes it easier for the water to flow inside the composite. When analyzing the water uptake of composites with fibers having different aspect ratios in comparison with non-treated bleach eucalyptus kraft pulp, we see that all composites with 40% bleach eucalyptus kraft pulp, here in the blue line, they have a water uptake increased by 26, 13, 39, and 23% in comparison in composites having cellulose 355 as a reinforcement. And that leads us to conclude the micronization procedure yields composites with inferior water uptakes. The reason behind these results is possibly due to the increased wettability of the shorter fibers, which leads to a decreased porosity. On its turn, the decreased porosity lowers the use of the water to permeate inside the composite. To conclude the results section, the melt flow rate assays show us that, regardless of the matrix, the increase in fiber load leads to a decrease in the melt flowability of the composites. Moreover, in these specific conditions, the PHB-based composites with a fiber load of 40% do not flow at all. However, when applying a different weight, all the PHB-based composites with micronized fibers flow, but composites with non-treated bleach eucalyptus kraft pulp do not flow. And that may be a consequence of the fiber shortening upon the mechanical treatments that may lead to a higher mobility of the fibers within the composite when in molten state. As for the composites with PLA, regardless of the use of different fibers having different aspect ratios, or even the use of bleach eucalyptus kraft pulp, the melt flow rate remains more or less unchanged. Now moving on to some conclusions of this work. From this work we can conclude that composites with micronized fibers displayed overall good dispersion and homogeneity, that reinforcing the composites with increasingly fiber load of micronized fibers led to an improved Young's modulus, tensile strength and flexural modulus, but on the negative side led to a decrease in the melt flow rate and an increase in the water uptake capacity. We can also conclude that composites with micronized fibers had considerably low water uptakes than composites with the non-treated bleach eucalyptus kraft pulp, and the PHB-based composites reinforced with micronized fibers, they had superior Young's modulus, tensile strength, flexural modulus, and the melt flow rate in comparison with the PHB-based composites reinforced with the non-treated bleach eucalyptus kraft pulp. Finally, I would like to acknowledge the University of Aveiro, CISECO and the Biopulpa Phone Group, and the Impact Project. And thank you all for your attention.
Yes, hello. So the subject is films from silent polyethylenamine with different mass ratio. We know that we have different amount of silence, depending on if they are considering softwood, hardwood, or gramineous plant. How we can make use of silane? One of the potential destinations of silane is packaging material. Why? Because the films from silane present a high gas barrier property. But silane films are very rigid and have tendency to crack, as we can see in the photograph. It has been shown that the controlled formation of polyelectrolyte complex obtained from silane and chitosan solution allowed to obtain a film that is homogeneous, flexible, resistant, and also has resistant under wet condition by considering the addition of silane solution and chitosan solution. The film is flexible, as can be seen here. And for instance, with 70% of silane and 70% of chitosan, we have a stress of 35 megapascals and a deformation of 11%. This is not so far from a polyethylene commercial polymers, at least in strength and elongation of the high density polyethylene plastic. Which are the limitations of this silane chitosan system? First, low solubility of both polymers, and thus too much water should be evaporated to obtain the film. And when a high silane chitosan mass rate is used, the stability of the complex is lost. So an inhomogeneous layer in a wet condition, and later an inhomogeneous film is obtained. We can expect that we could obtain a quencher rate in this system, because under the right condition, a dispersion of polyelectrolyte complexes can be separated in two phases, and quencher rate and a dilute solution phase. And these quencher rates contain a significant amount of hydration water. The size of this aggregate could be from few nanometers to 10 micrometer. But this process doesn't take place in the silane chitosan system. An aggregation or coagulation of the complex takes place. As a consequence, an homogeneous hydrated layer is formed, and later the layer turns in an inhomogeneous film on its right. Which alternative? We can consider to use another cationic polymer, but there is no cationic natural polymer other than chitosan. So we have to think about any kind of synthetic polymer. Ideally, a cationic polymer that we need that should be more soluble than chitosan. Under high silane content, a quencher rate can be separated from the supernatant phase, and these quencher rates should be useful to obtain a homogeneous film. Which is the ideal polymer? We can thought that a cationic polymer should have a lumbar mass and a branched structure. Why? In this case, we could avoid the aggregation or flocculation of the coacervate. One polymer that we can consider is polyethylenamine, because it's a branched lumbar mass cationic polyelectrolyte. It's used in paper-making industry and in other industries, and it's a low-cost cationic polyelectrolyte, but alone that does form film. In this work, the formation of film via polyelectrolyte complexes of silane and PEI is analyzed. First, the interaction between polymers at different pH is analyzed. The effect of silane PEI mass ratio from 50-50 to 90-10 at two different pH on the mechanical properties are reported. And for high content of silane, which leads to a phase separation, the formation of a film from the quencher rate is analyzed. We have used it for this work a silane rich fraction that was already extracted from sugarcane bagasse. Later, the fraction was precipitated from the liquor by ethanol addition at 1-to-1 volume ratio. And the composition, the precipitate was, of course, 67% of xylose, but 2% of glucuronic acid, and the 18% of arabinose. And also, the precipitate contains 13% of lignin. The molar mass of this silane was 56 kilodalton. And the polyethylene was a commercial polymer. The amine quantification by NMR spectroscopy show how much primary, secondary, and tertiary amine we have, which is necessary to know how is the structure, the polymer. And this polymer has a low molar mass because we can see that around 30% has a molar mass higher than 100 kilodalton. And the titration was made that it was a streaming current potential titration, made a different pH. We use a dilute silane solution that was added on a dilute pH solution. The ionic strength was adjusted. Later, for polyhydride complex preparation, we considered a more concentrated solution. And the styrene silane solution was added onto pH solution in a period of time of around between 20 and 30 seconds. And different mass ratio was considered. For high silane pH mass ratio, a quartile rate was separated from the supernatant solution. The composition of this supernatant solution was determined by colorimetric method, and film was prepared by casting operation method, and then it was tried at 40 degrees, and it was analyzed by tensile test using a standard method. First, we consider the interaction between silane and pH. We see here how is the potential, the streaming potential that is reduced when we add silane on pH solution. And we found here how is the mass ratio that correspond to the neutral condition. For different pH, this neutral mass ratio is reduced. For pH 4 and for pH 5, 6, and 7, the neutral mass ratio was similar, and it's a bit lower for pH 8. How we can see about the complexes. When we prepare a complex, we the size can be determined. In this case, for 70-30 mass ratio, we can see that the main fraction has around 1,500 nanometers, because we have a 3 mode in the side distribution, according to DLS measurement. So we can prepare the films and see how the films are, and we can see that all the films looks homogeneous. Here we have a film obtained from the whole solution, and this is a film obtained from the quartile rate. How about the mechanical properties? We can see that when we add more silane, we increase the resistance of the film. This is a certain effect of the pH. It's better for pH 7, but we have a drastic increase in the resistance in a mass ratio close to neutrality. Later, there's not too much difference. And if we consider the quotient rate, so separate the supernatant and prepare the film from the quotient rate, the properties are better. And the best situation is for 85-15 mass ratio. The strain at break has the opposite situation. It's reduced when we increase the amount of silence. And for the high silent content, we can consider the quotient rate, and the quotient rate shows similar stress at break. How is the composition of this quotient rate? We can see that this supernatant, that is 60% of the original volume, contain more pay than silent. So as a consequence, the mass fraction of the silent results higher in the quotient rate than the original suspension. Conclusions. The stream current iteration was useful to assess the polar interaction between silent and polyethylenamide. Neutrality mass ratio strongly depend on pH, but difference in ratio, low difference in ratio exists for pH between 5 and 7. The combination of these polymers show a good ability to film formation from moderate amount of silent to 90% of silent for both pH. The mechanical properties were clearly determined by silent content. A film of high strain at break can be obtained using low silent pay mass ratio, and a film with tensile stress resistance higher than 20 can be obtained, 20 megapascals, can be obtained when high ratio is applied. High silent pay mass ratio, for which an excess of negative charge exists, allow it to separate the supernatant to the quotient rate. In the supernatant, which is approximately 60% of the original volume, part of the original salt and a moderate amount of polymers are separated, and the film preparation from the quotient rate allowed to reduce the time and energy for film drying, and leads to the best value of a stress at break, that is around 35 megapascals, being the strain level enough for film handleability. Knowledge, we have to acknowledge to our founding institutions and to the whole research group. Thank you very much for your attention.
I am Agatha Gárate, and I am going to present this work entitled Bamboo as Non-Traditional Lignocellulosic Resource for the Nanocellulose Production, Zanuttini and Zanuttini angustifolia. It was carried out as part of the thesis to obtain the master's degree in Science and Technology of Fibrous Materials at the National University of Misiones. In Latin America, bamboo stands out for its fast and easy growth since it needs less water and pesticides than other lignocellulosic materials, which entails a lower maintenance cost. Its characteristics are similar to wood, which allows its use in a construction, shipboards, laminates, and floors. Despite them, it is not used on a large scale, and this is due to its little study and investigation of chemical and physical composition and uses that it can be given. In the present work, we attempt to value this lignocellulosic resource by nanofiber production. Two representative bamboo species from the north of South America as Zanuttini angustifolia and south of South America as Zanuttini are compared. The general objective is to value a rapidly growing resource of great regional interest, obtaining cellulose, hemicellulose, lignin, and structis as a source of high-value products. The methodology used was following. First, the representative sample of both bamboo species were cut and transferred to the laboratory. Second, the physical characterization consisted of the determination of basic density by ISO standard. Third, the chemical characterization was carried out under standard NREL analytical methods where total structures, total lignin, and structural carbohydrates, acetyl groups, and ash were quantified. And finally, the morphological characterization was carried out by the histological section analysis by optical microscopy and the study of cellular elements by FQA 360 fiber quality analyzer and optical microscopy. This scheme shows the treatment used to obtain two types of bamboo soda and anthraquinone pulps, with or without hydrothermal pretreatment to extract hemicellulose. You can also observe the methods used to characterize the bamboo samples, the soda and anthraquinone pulps obtained, and the nanocellulose produced from these pulps. Both bamboo species were treated with hot water to remove structures. These treated samples were divided in two parts. One part was treated by autohydrolysis hydrothermal treatment to extract the hemicellulose before the delignification, and the other was delignified directly. The delignification was carried out by soda and anthraquinone pulping. The resulting pulps were physically and chemically characterized by Weber magnet, alpha, beta, and gamma cellulose, residual lignin, degree of depolymerization, water retention capacity, and crystallinity. Then, a chemical pretreatment, tempo, and a mechanical treatment were then applied to both pulps to obtain nanocellulose, which was characterized by its carboxylic groups content and viscosity. In each of the liquid streams, we obtain hemicellulose and lignin on board together, which can be studied and valued to obtain another product. Now we will see the main result obtained. The basic density was determined for 36 square pieces of 25 millimeters on each side of three different parts of the stem, base, middle, and top, which were saturated with water for 36 hours, and the volume of the samples was determined by the Archimedes method. Then it was brought to the stop until constant weigh or dry weigh. The table shows the basic density of each species, which present significant statistical difference between the different parts of a stem. It was determined that the basic density range of both species were suitable for the pulp industry. We found that Guadua trini has a total extracted content slightly lower than Guadua angustifolia, almost 1%. Ash content was similar for both species, around 4%. Total liquid content was similar in both species, almost 24% for Guadua trini and 25% for Guadua angustifolia. The total carbohydrates content was almost 63% for Guadua trini and 64% for Guadua angustifolia. A summative analysis was carried out in which both species have a total percentage of components of 102%, which is encouraged because being close to 100% validates the characterization carried out. The analysis of the histological section of the small pieces of the stem was carried out from the thin lamina using a micrometer. We observed that the radial section of each species is in the measured in lenses of 4 and 10x of the microscope. We can see the vascular bundles and radio. In the same previous lenses, the images of the longitudinal section for each species can now be observed. We observe vessels, fibers, and cambium. Finally, in the cross-section, we can see vascular bundles, parenchyma, fibers, and cambium. As I mentioned previously, the determination of biometric data was carried out from a fiber solution, first using FQA fiber quality analyzer, which length and width distribution of fibers. The average fiber length was lower for Guadua trini. It was 1.044 millimeters for Guadua trini and 1.441 millimeters for Guadua angustifolia. The average width of fibers was slightly higher for Guadua trini. It was 24.4 microns for Guadua trini and 22 microns for Guadua angustifolia. Two different kinds of treatment were applied to both species to obtain cellulosic fibers. One involves a hydrothermal pretreatment to hydrolyze hemicelluloses, and the other involves a soda anthracynone pulping. The autohydrolysis conditions were the same for both species, as shown on the slide. The hydrothermal pretreatment was carried out to assess the pulp behavior in nanocellulose production and its properties when extracting with critical components as hemicellulose. Silane can be used to obtain other high-value products as xylitol and furfural. A stainless steel digester was used for pulping, which was heated in another small MK-type digester with automatic temperature, speed, and heating ramp controller, using water as fluid. The soda anthracynone pulping conditions are shown on the slide. In the sequential treatment, the autohydrolysis yield was around 78% for Guadu angustifolia and 79% for Guadu antrini. The total pulping yield was similar for both species, which was around 37%. In the samples without hydrothermal pretreatment, the pulping yield was significantly lower for Guadu angustifolia than Guadu antrini, that is to say almost 45% and 47% respectively. Kappa number indicates an indirect relationship of the pulp with the residual lignin. We can observe that there are differences between species and with and without hydrothermal pretreatment. We also see that Guadu antrini presents a better delignification behavior, having lower kappa number values in both cases. This table shows a higher fraction of long fibers retained in 30 mesh, around 37 to 52% of fibers for all pulps. Pulps with hydrothermal pretreatment present higher retention on this mesh due to the loss of minor fraction during washing in filtering. Alpha cellulose is related to the higher molecular weight fraction, which was higher in pulps with hydrothermal pretreatment. Beta cellulose is the degraded fraction, which was higher in pulps without hydrothermal treatment. And gamma cellulose is composed mainly of hemicellulose, so it is pretended in a lower content in pulps with hydrothermal pretreatment. The degree of polymerization was higher in pulps with hydrothermal pretreatment since they have many monomers in their chairs. There are no marked differences between species, although pulps with hydrothermal treatment tend to retain less water due to the removal of hydrophilic hemicellulose. The crystallinity of the pulp was obtained using X-ray diffraction equipment, and the crystallinity was calculated with the equation shown. The crystallinity in both species was higher than 80% and higher in pulps with hydrothermal pretreatment. This result can be attributed to the lower amount of hemicellulose present in these pulps, which have an amorphous structure. In the graph, we observe the characteristic diffractograms for both species with and without hydrothermal pretreatment. These typically represent semi-crystalline materials, and the peaks are located in the same position in all species between 22 and 23 degrees. There are various methods to obtain nanocellulose. We choose a chemical pretreatment of tempo oxidation and then mechanical nanofibrillation in a colloidal mill. The tempo oxidation conditions for 10 grams of dry sample were 10% sodium bromide, 1.6% tempo, and 5 mmol sodium hypochlorite. First, the sodium bromide and tempo were dissolved for a half an hour, then the pulp and sodium hypochlorite were added, maintaining a pH of 10 to 10.5 with the help of sodium hydroxide. When the pH is kept constant without using sodium hydroxide, the reaction is over. The resultant was washed 3 times with 2 liters of water to remove the alkali and brought to 1% consistency, then passed through to the colloidal mill 10 times. This nanocellulose obtained was also characterized. Carboxylic groups were obtained through conjugated fractation. The amount of carboxylic group per gram of dry pulp indicates the degree of oxidation with the tempo treatment, since they generate repulsive force among themselves, which favors the wall-to-death structure, and this is higher in both species in pulp that did not undergo hydrothermal pretreatment. Both species viscosity was determined using 100 milliliters of the sample at 0.3% consistency at 500 rpm for 60 minutes at 25 degrees. The graph shows the viscosity values versus the shear speed. For both species, the viscosity is higher in nanocellulose obtained from pulps without hydrothermal treatment due to a more significant hemicellulose presence. They have a higher yield of nanocelluloses and a greater capacity for the individualization of nanofibers. In the graph, we observe the correlation between the content of carboxylic groups generated in temp oxidation and the viscosity of the nanocellulose suspension in water. It presents a correlation coefficient of 96%, which indicates that the relationship is significant and positive. Since the nanocellulose from without hydrothermal pretreatment pulps are closer to the trend line, they present a better behavior for nanofibrillation. Now we are going to see the conclusions. Both species have densities that are within the proper range for the pulp industry. The two species present average length greater than 1 millimeter, similar to broadleaves such as eucalyptus. Both species have similar carbohydrate content. The hemicellulose content was also similar in both species, composed mainly of xylem, in the same way with the ash content. The lignin and extractive content of guaduatrini were slightly lower. The hydrothermal treatment extracted 20.8% of hemicellulose in guaduatrini and 21.8% in guadu angustifolia. The total pulping yields of both species of material with hydrothermal treatment were lower than the total yield of untreated material. Based on kappa numbers, guaduatrini showed better behavior to the lignification, and it is not so affected by hydrothermal treatment as pulpers soda and traquinone. Soda and traquinone pulps without hydrothermal treatment of both species presented similar alpha cellulose contents. The alpha cellulose contents were higher in the pulps with hydrothermal treatment, also similar in both species. The crystallinity index of both species pulps with and without hydrothermal treatment was high, more than 80%. The highest crystallinity of the pulps with hydrothermal treatment is attributed to the fact that these pulps have a low hemicellulose content. Nanocellulose tempo could be obtained with all kinds of pulp. The effect of the type of species and pretreatment in obtaining pulp of the thickness distribution of the nanofibers will be analyzed later. Based on the carboxylic group contents, it is concluded that the guaduatrini species without hydrothermal pretreatment has the highest amount of acid group for each gram of dry sample. Viscosities of aqueous nanocellulose tempo suspension were higher for the solutions obtained from soda and traquinone pulps without hydrothermal treatment. It would indicate that the aspect ratio of the nanofibers obtained from pulps with low hemicellulose content were lower.
To the speakers for their interesting papers. Now we have some time to questions. I have already here some questions that I will to the speakers. So for Bruno, the first question is how to relate the thermodynamic compatibility of cellulosic fibers with PHB and PLA. Bruno, please.
Good afternoon, and thank you for your question. So regarding the compatibility, we know from the literature that the PHB is a more hydrophobic polymer than the PLA, and as such, compatibility with hydrophilic cellulose is inferior with PHB. We confirmed the superior compatibility of fibers using electronic microscopy, and then of course those results that I showed in the presentation actually confirm the superior compatibility because we have better properties with PLA than when we use PHB. I hope that answers the question.
Yes.
Mr. Chairman, is there anything
Okay,
wrong with
sorry.
the transmission?
Sorry, I was in mute without taking notice. So, again, for a question for Luis, could these lignin nanoparticles be used as UV protector in textile applications?
Well, this is one of the objectives we have. We intend to continue this research by preparing films and could be used for that purpose. But up to this point, all we have in this research is the measurement of antioxidant activity.
Okay, thank you. And one question for Miguel. What solvent did you use to solubilize and distract Chilean? Was it stable? What method of characterization did you use for molecular rate determination of the Chilean?
Yes. The cyanide was extracted by alkali, just on water, and it is stable, and it's, as I explained it was precipitated by alcohol, but using only 1-to-1 ratio between this solvent, no more than that, because it's to reduce cost. And after that, silane is characterized, for instance, the molecular mass was determined by, in this case, by SEC determination, by chromatography. Yeah.
Okay, thank you. Now we have a question for Agatha. What is the difference in the yield of NFC from eucalyptus wood and bamboo?
Excuse me, can you write a question, because my English is not so fluid as I want to, so.
So
Yes.
now we are equal. Okay, what is the difference in the yield of NFC from eucalyptus wood and bamboo?
The difference between the eucalypt and bamboo, about what?
The yield,
Excuse me.
the yield
The yield.
compared with eucalyptus wood and bamboo.
About nanocellulose? You
Yes.
mean? My thesis was about bamboo. The eucalypt, I don't have the exact yield about it, but I know that it's in the range of gramineas. Bamboo and eucalypt is in the same range.
Okay, thank you. So we have other question for Luis. How important is to have lignin and as nanoparticle in antioxidation applications?
Yeah, that's an interesting question. Thank you very much. As we saw for the Trolox controls, the behavior was constant with time. And with the lignin, we noticed that the antioxidant properties, they increased with time, which means that more groups, active groups, are made accessible with time as the solvent and as the material gets in contact with the solution in which the radicals are formed. So this is an advantage because, of course, because of the high surface area and also the number of different chemical groups that are present in lignin, then one may envisage a higher antioxidant behavior as go by, and therefore the medium in which it is used.
Okay, thank you. I think we have time for more 1 or 2 questions. Another question for Agatha. what is the average time to have Gadua Trini ready for collection?
For collection, 4 years. The Guadua in general, Trini or Angustifolia is ready in approximately 4 years.
Okay, thank you. Luis, another question. What solvent was used to determine the antioxidant activity with ABTS? That's one question. The other one is, was the same solvent used for the reference lignins in comparison?
The antioxidant properties were measured in water, in TPS buffer. Whereas the solvent, as I understood from the question, is this related to the solvent that I used for preparing the nanoparticles? The nanoprecipitation? Maybe I missed that from the question. Can you repeat it, please? Because what is this solvent related
Was the
to?
same solvent used for the reference lignins in comparison?
Of course, yeah, of course. All the different controls that we made in our research were done in the same condition.
Okay, thank you very much. I think we have reached all the questions. So, and we are in our time, really some minutes more than the time schedule. So we have to thanks to the colleagues that give this and this nice speeches and this good information and papers. So thank you very much all. Have a nice rest of the day. Thank you very much.
Okay.
Thank you very much.
Thank you.
Thank you.
Bye-bye.
Bye.
Bye.